This begins the second part of chapter 2. We're going to be talking about the basic elemental formats of how we get a chemical formula, what a chemical formula is, and how to name them. So when we start, we need to talk about the atomic mass and average atomic mass. When we talk about masses of elements and compounds, we're literally just talking about how much stuff takes up a certain amount of space, kind of like density. For this chapter and this chapter only, we are going to be referring as atomic masses as the atomic mass unit. And we can use the carbon-12 atom as kind of our standard form. So all this basically means is if you look at a periodic table, each element has a mass there, but the mass you see on that periodic table is actually an average of all the isotopes of that element that exist. So you guys have heard of carbon dating. Carbon dating uses carbon-14, where carbon-12 is a carbon with a mass of 12, where carbon-14 is a carbon with a mass of 14. Go here. Bazinga! So, sorry, that was my phone. When you look at carbon, again, we talked about there being different types of carbons, meaning 2 or 3 different carbons will have the same number of protons, different number of neutrons. So in order to figure out what's happening and what the average mass is for carbons, we have to take into account the percentages of each isotope of the element. So an isotope, again, are 2 of the same elements that have different number of neutrons, same number of protons. So if we look in the world, if we were just to have all the carbons in all the world in a big bag, and we were to stick our hand in and grab one, the probability of us pulling out a carbon-12 is 98.93%. So we're going to go through and learn this as by working a problem. So oxygen, we can say that there are 1, 2, 3 different isotopes of oxygen, meaning they are all going to have 8 protons, but you can see based on their masses from the notation that their masses differ. Their masses differ because even though they have the same number of protons, they all have 8 protons, their masses differ because they have different number of neutrons. And what this problem is telling us is that for oxygen, 16, its abundance in the world is 99.757%. Oxygen 17, its abundance is 0.038%, virtually none of them. And the oxygen 18 is 0.205%. Okay, their atomic mass units are respectively 15.9949, 16.9991, and 17.9992. Now, if you look at the mass of oxygen on the periodic table, if you just look in your book at the front cover, it has oxygen listed as an atomic mass of 16.00. Now, that's a highly rounded out number, but if we were going to calculate the average mass, meaning including all the isotopes that are present and their abundances in the world, all we do is follow the same setup. So I don't like the way your book has this written out here in these slideshows, but it's always going to be the abundance in your percentage to a decimal times the atomic mass unit, and it's going to give you some number. Okay, so if we took 16 oxygen, 17 oxygen, 18 oxygen, and we put in their abundance, this one was 0.98%, I'm sorry, 0.98, that's the, into a decimal. And I'm kind of just remembering the numbers because if I click back, all my writing will go away. 17 was, oh gosh, that was 0.03, so that turned into a decimal. That's 0.0003. Okay, this mass was, I believe, 16.99. And then 0.205 into a decimal. That is 0.0025, and its atomic mass unit was 17.99. Now, if we multiply all these out, I'm going to do that right quick. So 0.9, I think it was 98, times 15.9954. We're going to get a number of 15.963. Okay. Oh, hey, look at that. These numbers were right here, and I've just totally ignored them. I do that sometimes, y'all. Then we're going to take the second one, 0.00038 times 16.9991, and we get 0.006. And then the last one is 0.044975. If you were to just add all these together, this is approximately what you get. You're going to actually get 15.9954-ish. And we round that up to 16. So this is always going to be your setup where you have your abundance, or the percentage that's converted to a decimal, your atomic mass unit, which is going to be given. You're going to get the number, and then you add it up, and this number right here, whatever this adds up to be, that's the number you see on the periodic table. It takes into account all the isotopes of each individual element. I want to remind something of you. If you are given two isotopes, one atomic mass unit of one isotope, an abundance of one isotope, and then only the atomic mass unit of the second isotope, you can simply find the percentage of abundance of the second isotope by simple subtraction from 100. So when we talk about atomic ions, what we are talking about are neutral elements on the periodic table that have gained or lost electrons. When you lose electrons, we call that a cation, and it is positively charged because we are losing negativeness. So what do I mean by that? Well, let's just take a look. Let's just pretend here's my nucleus, and that's where my electrons are going to be. I'm ignoring main energy levels just for the purposes of showing you this. So if I have something that has 3 protons and 3 electrons, this element is neutral. Okay? The negatively charged electrons cancel out the positively charged protons. But if I take one away, if I take this electron and it goes away, okay, then what I'm left with are 2 negatives and 3 positives. That means my net now is +1. Overall, there's a +1 charge. When you lose negativeness, you're becoming more positively charged. The reverse would be true if I added electrons. Okay, if this were an element that gained an electron, let's just go back to the original. So here's my original. Now if it gains one more, now I have a total of a -4 charge, 1, 2, 3, 4, and still only 3 positively charged protons. Now we're going to be overall a -1 charge. So when we become an ion, when an element becomes an ion, it is no longer neutral, and it is no longer neutral because it either gains or loses electrons. When it loses an electron, it becomes a cation, that's what we call it, and it is positively charged. Metals are the ones that will lose electrons. Non-metals gain those electrons. Non-metals, when they gain an electron, become negatively charged because they have extra electrons. They've picked up electrons from something else. We call things that are negatively charged because they're an ion, we refer to them as an anion, and those are generally our nonmetals. Remember, we said metalloids could kind of behave either like a metal or like a nonmetal depending on what they're reacted in. Well, this is where that part comes into play. Will it gain or lose electrons? Will it play or act as the anion or the cation? It just depends. We can see aluminum is 3 plus. It is in group 13, so group 13 metals have a 3 plus charge. Oxygen, it is in group 16. All group 16 nonmetals have a 2 minus charge. That aluminum and oxygen have these charges. So the simple trick is simply to do what I call a switcheroo. The number only from the other thing gets put with the previous thing. So what do I mean about that? The 3 only, not the plus, just the number 3, goes to the oxygen, and the 2 goes to the aluminum. So that tells us that there are 2 aluminums and 3 oxygens present in this compound. If it is a polyatomic, then we still do the same thing. Remember, PO4, the whole thing is a 3 minus charge. So we take the 3 and we give it to the calcium. I know the calcium is 2 plus because I've looked on the periodic table and seen that calcium is in the group 2, and all of group 2 metals have a plus 2 charge. I know that phosphate has a minus 3 charge because I looked at my cheat sheet for my polyatomics while I'm starting to memorize them, and that's what it tells me. And then the 3 goes to the calcium, but then the 2 goes to the phosphate, but it's the whole phosphate. Okay, this whole thing gets put in parentheses because I have to show that there are 2 of them. So when we talk about this, we're talking about these formulas in terms of chemical formulas and molecular formulas and allotropes. So the chemical formula just tells us the composition of the substance, what is in the substance. The molecular formula tells us how many of each element is in the chemical formula. An allotrope is just 2 or more distinct forms of an element. So for example, the element carbon, it can be both a diamond that we wear in our jewelry and we love, or it can be in the form of graphite, which is that stuff that you write with your pencils with. Okay, the lead for your pencil is graphite. They have clearly different properties, where diamonds are beautiful and shiny and glitzy and hard and solid, and graphite is very powdery and rubbery and writes on things, and just has very different properties. Here is to do the reverse switcheroo. Okay, reverse switcheroo. So what does that mean? Remember we said, okay, if I had hold on, let me just erase that. I want to write aluminum. Remember when we looked at the aluminum, we said Al3 plus and O2 minus, and we just brought them down, right, to get Al2O3. Well, the reverse of that is going whoop, whoop. It must be, for example, here, it must be that it's Fe3 plus, because I took this 3 and just put it with the iron, and then the 2 in my reverse switcheroo would make oxygen 2 minus, and I know that's true because oxygen is a representative element. It is in group 16 on the periodic table and always has a minus 2 charge. Okay, so if oxygen always has a minus 2 charge, how do we figure this one out? Well, FeO, it's not a subscript of 1 and 1, it's really FeO, right? There's really a 2 here with this iron. Why? Because we know oxygen is always 2 minus. So if we had done the switcheroo, the 2 from the oxygen would have gone on the iron. We can see that they are 1 to 1. So it must be that this iron is 2. Because if we have Fe2O2, that is the same as saying FeO, because we always have to have the lowest common whole number subscripts. okay? But what if I can't just do a switcheroo very easily? What if I'm unsure? What if there's an overall charge on the whole entire thing where I'm trying to figure out the transitional metal charge? Well, I'm going to give it basic algebra, okay? Here's my basic algebra. I know that a chloride ion is a -1. I know that because if I look on the periodic table, I can see that chlorine is in group 17, and all of group 17 nonmetals have a charge of 1- all the time. I also know that there are 4 of them because it tells me that. Okay, my compound tells me that. I'm trying to figure out the manganese, have no idea what it is. And I know that there's 1 of them because when there's no subscript written, it's assumed 1. So now that I have 1x plus 4 times -1 equals 0, it equals 0 because the overall charge is 0. I know the overall charge on the whole thing is 0 because there is no charge written on the outside of MnCl4. So then I just simply solve for x, basic algebra. This sheet is uploaded for you to reference, and there is a few other examples on that reference sheet in the helpful information. Now, we are also going to be using Greek prefixes. You need to know these through the number 10. And, you know, mono, di, tri, tetra, penta, etc. You need to know these through 10, and we're going to learn when to use them in just a minute. Here's just some examples of some compounds that use the Greek prefixes. You know carbon monoxide and carbon dioxide. That mono means 1, right? 1 oxygen, and di meaning 2. So if we go to ternary ionic, ternary meaning 3, that means there's 3 individual elements. It's usually a metal, a nonmetal, and something else. And typically that metal and something else, a nonmetal and something else, is a polyatomic. Generally, that's the rule. So how we name these is we name the metal cation first, and then we just name the polyatomic. By the way, NM is what I abbreviate nonmetal with. So if I look at the first example, I have 1, 2, 3 separate entities, 3 separate elements. Again, don't care how many of them I have. And if you go to your polyatomic list, you will see that SO4 is sulfate. I know that because I looked right on my list. Okay, so in this case, we name it sodium sulfate. Mg, P, and O, my 3 different separate elements. You will see if you look on your list of polyatomics that PO4 is phosphate. And I would just name this magnesium phosphate. You'll note for the transitional metal also, copper, I use the Roman numerals to indicate which copper I have. In this case, I have copper 2, and it's copper 2 nitrate. Binary molecular, now we're getting to the moleculars. Again, binary meaning 2, and molecular meaning they're both nonmetals. Okay, this is where I use those Greek prefixes. So the first thing you name using a Greek prefix if necessary, meaning the first word does not need mono, but the second word will if there's only 1 entity. Okay, so you use your Greek prefix and name the first nonmetal as is. Then you do the Greek prefix, need a mono if it's necessary, and write the second nonmetal name, changing to an IDE ending. So the first example is Br308. Here's my first entity, my second entity, my 2 individual elements, binary, and they're molecular because it's molecular as opposed to ionic because both Br and O are nonmetals. I looked right at my color-coded periodic table to figure that out. So there are 3 Brs. So I need the Greek prefix tri. Okay. Then I'm just going to name what it is, and it's boron. So it's the first name. Then I see that the oxygen has 8. So I'm going to use the Greek prefix octo. And then I'm going to name with the IDE ending. It's octaoxide, okay? And that's how I get it. So if I go to the second one, P2O5, I need two, or I don't need to, I have two, so I need di in the name. Diphosphorus, di meaning two, diphosphorus, pent meaning 5, oxide. Carbon dioxide, note I did not use a mono because mono is not used on the first nonmetal. It's only used with the second nonmetal, the second part of the name, as in carbon monoxide. You'll note it's not monocarbon monoxide, it's just carbon monoxide. Binary acids, again, binary meaning two, acid meaning it's going to be the hydrogen and a non-metal with a parentheses next to it aqueous. The AQ. That AQ just means it's an aqueous solution. So we name these by using the word hydro, naming the non-metal, and adding the ic ending, the IC ending. So HCl, H for hydro, Cl, chloro, with an ic ending. So hydrochloric acid. HBr, hydrobromic acid. Ternary oxyacids, ternary again meaning three, oxyacid meaning a hydrogen, a nonmetal, and an oxygen. Typically that nonmetal and oxygen are a polyatomic of some kind. Here's the rule. Know this. If ate, then ic. If ite, then os. What in the world are you talking about, Miss Meriwether? If ate, then ic. If ite, then os. So when we name this, we're dropping the hydro, even though these are acids, we're dropping the hydro, and we're going to change the ending to either ic or os based on the name of the polyatomic. Okay, so if I look at H2SO4, I see 1, 2, 3 different entities, ternary. That hydrogen out in front tells me it's an oxyacid. If it were a metal out in front, it would be a ternary ionic, but it's not, it's a hydrogen, so it's an oxyacid. The S and the O make up my polyatomic, the SO4 make up my polyatomic. I know that because I'm becoming very familiar with them and can recognize them in a compound. So my SO4 is sulfate. This oxyacid is derived from the sulfate polyatomic. If ate, then ic. So it's sulfuric acid. We drop the hydro, name the polyatomic, and change the ending to either ic or os. Okay? If I compare that to this example, SO3 comes from, or not comes from, is sulfite. How do I know this? I looked right on my list of polyatomics. So it's ite. If ite, then os. So instead of having sulfuric acid, we're going to have sulfurose acid. Okay, if ate, then ic. If ite, then os. Now we have hydrates. Hydrates are compounds that are generally ionic compounds that are bonded to water. There's water as part of their structure. Okay, so the way we name these is we simply name the ionic compound just like we would any other ionic compound, whether it's binary or ternary. In this case, we have a binary one for the first example. 1, 2. It's two separate elements. They are both a metal and a nonmetal, so it's a binary ionic. And I name binary ionics by, excuse me, naming the first metal, the cation, naming the second thing, the anion, with an IDE ending, so barium chloride, and then I use Greek prefixes. So for number 2, I get di, And then the water is indicated by the word hydrate. So barium chloride dihydrate. The second one, lithium chloride monohydrate. There's no coefficient in front of that water, so it's understood to be 1. There's no coefficient there. Nothing for me to box off. Manganese sulfate, heptahydrate. Go through these practice examples. I'm not going to do them with you. Go through them in the PowerPoint and see if you can figure it out. There are also several worksheets up for you to practice if you need more practice, and the key is completely written out.